Hello class, let's continue our discussion on some principles that we need to be aware of as we're designing syntheses when we want to put substituents on a benzene ring. So let's take a look at this molecule right here. And so let's say we want to make this molecule. Now, we have to be very, very careful in which order we add these groups. Okay. So let's just think through this. If I started with a benzene and I did the bromination first, we would then get the bromine, right? Right there. Perfect. And then if we try to do the nitration with some sulfuric acid, what would our product look like? Halogens are what? Electron withdrawing, but they're orthopara directors. So we are going to get the majority, a lot of the product like this in the para and ortho positions. That's not what we want. We want it in the meta position. So if we redo this, what if we replace the order? What if we change the order up a bit? What if we did the nitration first? What would that do? That would put the nitro group on, right? And then if we did the bromination, that is the electron withdrawing group, meta director, and then it would attach the bromine on the meta position. And look, that is our compound. I originally drew it like this. Like that. But do you see how this in green is the same thing over here? It's just rotated. So isn't that cool that we have to think about the order in which we do the synthesis, because the order is going to determine the regiochemistry of our product. Really cool thing to keep track of. Let's take a look at another consideration and another example. Okay. When we take a look at this molecule right here, this is our target molecule that we want to synthesize. We'll notice a couple things. One, the orientation or the regiochemistry here is meta. So we need a meta director. So if we consider putting on the chlorine first, we've just watched how that is an orthopara director. So that doesn't work, right? But if, let's say, we attach somehow, what if we attached that piece first? Okay. What type of director is that guy? Well, that's an orthopara director as well. So in this case, if we install this one, the chlorine first, we're going to get an orthopara director. Or if we install an amine, we'll get an orthopara director. So we're just like, what do we do now? Well, we have to remember something, that in order to make amines, we typically started with a nitro group, and then we reduced it to the amine. It was a two-step process. So if we remember that, what if we started with the nitro group? Right. What if we do the nitration? We would get the nitro group. That now is ortho-para directing. Sorry, meta directing. So we could do the chlorination And then that will go to the meta position. All right. And then we just have to do one more step to reduce, well, actually 2 more steps. It takes 2 steps to reduce the nitro group into the amine. And we can represent that by the first reaction. We add some zinc and some hydrochloric acid. And then step 2, we would have to do a basic workup to give us our amine. So isn't that also so cool? Our target compound right here in this particular example had to come from a previous group, which was the nitro group. Let's see what's next here. So now let's talk about some limitations that you need to be aware of. Okay. What if you wanted to do something like this? You already have an amine on there. And let's say you want to put a nitro group on. So you want something to look like this. And nitro. Okay, that's the compound that you want to make. So there's some limitations here that we need to be aware of. And that is when you have amines. If you want to take an amine and do a nitro group, these conditions right here cause some major problems for the amine group. The first issue that you need to be aware of is this is a very oxidizing environment, and that environment will oxidize the amine. So at the end of the reaction, you won't have an amine here. You may have a nitro group on the benzene, but this guy is all messed up now. So that's the first thing that you need to be aware of. The second thing that you need to be aware of is that, let's just say hypothetically, if the amine was not oxidized, you are under extremely acidic conditions. So with that much acid there, you are actually going to protonate this guy and turn it into a positively charged amine, quaternary amine. So what does that mean? Not quaternary amine, scratch that. So we have this positively charged amine. Now that is a meta-director. And so now that introduces other complications. Now that's going to be a meta-director when you wanted it to be a para-director. So things to be aware of with amines on the benzene ring. Okay, so those 2 considerations you need to be aware of them so you don't make some mistakes. Okay. Okay, so we have some other limitations that I'm going to erase this board so we can look at it that way. The next limitation we need to be aware of is, let's say we have these 2 molecules and we wanted to do a Friedel-Crafts alkylation or a Friedel-Crafts acylation. That's what's right here, the conditions for those, the Friedel-Crafts. So Friedel-Crafts acylation or alkylation. If you try to do this reaction or this starting material with Friedel-Crafts, you would get no reaction. And if you tried this guy, did the reaction, you get no reaction. Now what can you see about these 2 groups right here? They're electron withdrawing, so they're deactivators. This one right here is a moderately deactivating group, and this is a strong deactivating group. So if you ever want to do a Friedel-Crafts acylation or alkylation and you have a strong or a moderate deactivating group, it just doesn't work. Nothing will happen. But if you had a very, very weak deactivator, then yes. Another consideration to be aware of. We now want to move on to another reaction type that we need to be aware of. Okay. And that is nucleophilic aromatic substitution. Nucleophilic aromatic substitution. Okay. And nucleophilic aromatic substitution can be represented with this little symbol. You remember SN2, SN1, and things like that. That's what that stands for. Okay. So nucleophilic aromatic substitution. That's what the S stands for. Now, what does this reaction look like, generally speaking here? It's when you have a benzene ring and you have a really strong electron withdrawing group, typically a nitro group, and you have a halogen. And when you take that molecule and treat it with a strong base, okay, and you heat it up 70 degrees C, and then you have a acidic workup at the end of the reaction, what's going to happen is we're going to just replace this bromine with the OH. Of our nitro group there and our OH. So we have substituted in the OH for the halogen. Okay? That's the overall process for a nucleophilic aromatic substitution reaction. Now, if we take a look at these conditions here, we have some rules here that we need to address. Okay? The first thing that you have to have in order to get this reaction to work is you have to have a very strong electron withdrawing group, typically a nitro group. And then that nitro group has to be in the para or ortho position in order for this reaction to work. If this electron withdrawing group is on the meta position, it does not work. And we're going to go into the mechanism to understand why that's the case. But I'm just up front telling you, the electron withdrawing group has to be para or ortho in order for this nucleophilic aromatic substitution reaction to work. Another consideration is that you have to have a good leaving group. And typically those are going to be the halogens. Okay. Okay, so if I redraw this and put the nitro group there, this does not happen. Okay, I'm just really hammering that idea home because it's so important. The meta position, no. Okay? Now the reason why has to do with the mechanism. So let's jump into that and we will understand what's going on, okay? Okay, now when we look at this mechanism here, let me explain what's going on. Here's our starting material, and we're going to react it with our sodium hydroxide, represented with just OH. Everything here in green right here is resonance structures. But these resonance structures have a name called the Meisenheimer complex. And now this Meisenheimer complex may look very similar to when we were looking at the sigma complex. Recall that the sigma complex was with the electrophilic aromatic substitution reactions. But what's the difference between the Meisenheimer complex and the sigma complex? And the big difference, okay? The Meisenheimer complex has a negative charge going through the ring, whereas the sigma complex had a positive charge going through the ring. So that's the difference. And then here in blue, that is our product. So we go from this orange molecule to this blue one. That's our product. And I've noticed that I've cut off some of the molecule. So I'll draw it. It's simply just the nitro group right there. So let's just go through this mechanistically so we can see the arrow pushing, so we can understand what's going on here. Right? Okay, so what's going on here? This is going to come in, attack that carbon there, and then take these pi electrons and stick them on that carbon to give us this intermediate right here. Now in the Meisenheimer complex, we are just moving the electrons around in this manner. So now we have a negative charge on here. Now you can see that's pretty stabilizing, right? Because this is electron withdrawing, so it can pull the negative charge out of the ring to help stabilize that. But then to go to the next resonance structure, we have this, like so. Gives us the negative charge here. And then we have another resonance structure in which we can bring those electrons back down, like so, and then take these electrons, put them there, and that will bring that guy right there. So it's really technically in this resonance structure right here where we remove the negative charge from the ring. You can see the negative charge goes from here to the oxygen atom right there. And then to go to our product, what happens is that we're going to eliminate the chlorine atom. So this is going to collapse, the low pair is going to collapse back down, like so. And then these pi electrons will come here. Those will come there. I just made a Texas carbon, so I need to break that bond right there. So we would get the plus the chloride right there. And we eliminate off the chlorine to give us our compound right there. So that's the mechanism for this transformation. But remember the difference between the sigma complex and the Meisenheimer complex. Meisenheimer complex has the negative charge going through. Sigma complex has the positive charge going through. Okay. Now you may be wondering, why does the nitro group have to be on the para or ortho positions? Well, it has to do with the fact that you need to stabilize that negative charge. And it stabilizes that negative charge by bringing that negative charge out of the ring onto the oxygen atom right here. And that can only happen when the electron withdrawing group is in the para and ortho positions. If you take that nitro group and stick it on the meta position, there's no way for the electron density to go onto the oxygen atom in the nitro group. I'm not going to draw that out for you, but that is a really good exercise for you to do if you want to see why the meta position does not allow this reaction to work? I already told you the answer, but if you want to work it out and show using mechanisms, I'd highly recommend taking the time to do that. Okay. Now, when we do this reaction, now remember, with this reaction, there has to be some heat present, right? That's the first step. But then you have that second step where you have to do the acidic workup. And the reason why you have to have that second step is because in the first step, you are under basic conditions. And under basic conditions, the phenol right here is pretty acidic. And so what you're going to have is under basic conditions, your product after step 1 right here is actually going to be the alkoxide. And so you have to have that second step with the acidic workup to protonate the alkoxide to get it back to our product. Okay? So yes, we originally formed our product, but we're under basic conditions, so it deprotonates it. So we have to add acid to get it back to our product. Okay? So after we do that step, we'll go back to this guy right there. So you need to be aware of that so you don't get don't freak out or get confused if you see that second step. That's why it's there. Okay, so this whole scheme right here has a special name, Nucleophilic Aromatic Substitution reactions. Okay, and that was different from what? The electrophilic aromatic substitution reactions, right? So now I want to look at another type of reaction. Now what I want to do is just write a few reactions here and highlight some things here. So let's say if we have a bromine there, nitro group. We just went over that if you took sodium hydroxide, and then that's step 1, and then step 2, you do your acidic workup, you would get a substitution, right? And this reaction proceeded via nucleophilic aromatic substitution mechanism. However, if you try to take this reaction right here, did the same conditions, we would get no reaction, right? And we get no reaction because we don't have an electron withdrawing group on the para or ortho position. Okay? But what if, and I'm forgetting one thing, that's important to note, that it does require some heat, 70 degrees C, to get that reaction to go. But what if we had that compound right here, okay, and I treated it with, let's see, sodium hydroxide, step 2, an acidic workup. But this time we just changed the temperature from 70 degrees to, let's say, 350 degrees. Like really crank up the heat. In those conditions, we do get a reaction that occurs. We can replace that halogen. But what's different from this one in pink and this one up here is the mechanism is different. The one in pink actually proceeds from a different mechanism, and we call that mechanism the elimination-addition mechanism, or elimination-addition reaction. It's probably the better way of saying it. So it's kind of interesting that this reaction right here at 70 degrees does not work. But if we crank it up to 350 degrees, it does work. But it proceeds via a different mechanism than this one right here. So that's really cool. This is going to be kind of crazy on how this mechanism works, okay? And so we'll talk about some other examples and go into the mechanism here. Now, what can make this reaction work even better, okay, is if we replace that sodium hydroxide with a stronger nucleophile. Because the OH, what came from sodium hydroxide and is a very strong nucleophile. But we can make even a stronger one. Sodium amide, and then that reaction would be done in liquid ammonia. And then you would have a acidic workup at the end. So what would happen if we changed it to those conditions? You can see now we're going to get our amine like that. Now this reaction right here undergoes this transformation via elimination-addition reaction. Okay. Now, how do chemists know that there is a different mechanism from this type of reaction to this one? And it's a really cool experiment. It has to do with isotopic labeling, which I'm going to erase this board and then show you what that's all about. That kind of gives us an idea that there's a different mechanism that's going on here. So I think this experiment is really cool. So what we do is we take this starting material and we isotopically label that carbon, and only that carbon, with a carbon-13. And then we proceed to do the reaction. And we can track where that carbon is in the product. If this reaction did the substitution, or don't want to mess this up here, the nucleophilic aromatic substitution mechanism, we would only get this product. The nitrogen or the amine would replace or substitute the bromine. Okay? That's if we use the nucleophilic aromatic substitution mechanism. That's our only product. But lo and behold, and the reason why this would be the only product goes back to the mechanism. Go back to that mechanism. Watch how I draw those arrows on how that the nucleophile comes in and attacks. It would only attack that carbon. And you can see that when you look at the mechanism. But in this experiment, what we observe is this product, where the nitrogen attacks the non-labeled carbon. And that can't happen if we're using the nucleophilic aromatic substitution mechanism. But because we're getting this type of product here, the mechanism is different. And so that's what I want to show you now, is how does that work? And the way that it works is there's this really funky intermediate called a benzyne intermediate. Okay? So let me show you how that's going to work. Okay? So when we have this molecule here, our first step in the mechanism, let's clean this up a bit, is that we're going to have, let's get the right colors here. We will have, let's say, a hydrogen right here. Let's draw that hydrogen there. Okay. And then this species, goodness, let's clean that guy up. Actually looks like this. All right, negatively charged species. And that's going to come in and attack that hydrogen. That's what bases do. Okay. Now, where's those electrons going to go? Well, let's draw this out first. I like that. Look at what happens here. It's going to take these electrons right here and place it on that carbon like that. So now what we're going to get is a species that looks like this. Like that. And it would be negatively charged. Oh. And then that lone pair right there is going to come in and kick off the bromine. It's going to come in like this and kick off the bromine. Now the bromine has 3 lone pairs, and when that kicks that guy off, now this first step right here, let's make sure we understand that. That first step right there is going to be reversible. And then this part right here, what's going to happen now? What's that going to look like? Boom. That is crazy looking. That compound right there is called the benzyne. That's our benzyne intermediate. All right. Now with that benzyne intermediate, what's going to happen is we are going to have more of that species present, and that's going to attack one of these carbons. And if we were following the isotopic labels, okay, that nitrogen species can attack at this carbon or that carbon. It does not matter. So if we show it attacking, let's say, this species right here, what would we get? So now that's going to form a Texas carbon if we don't move some arrows, right? Or move some electrons. So we've got to put the electrons back right there. So then we have, let's see, double bond there, there, there. We have our NH2 there, and negatively charged right there. And then we're going to have our proton transfer, because the condition has liquid ammonia here. So this is our proton source. All right, there's our proton source. And so then this guy's going to come in, grab our proton, just like that. And if we're keeping track, it added there. But remember, we do have this species right here. And we can have that species. Why? Because this amine right here can come in and attack on that carbon instead, bringing the electrons over there. All right? So that's the mechanism that explains why you can get 2 different products, because of this intermediate right here called the benzyne. So this mechanism that I showed you is going to be the same exact mechanism if you were using the OH. If you're using sodium hydroxide, very, very similar mechanism. Okay, the benzyne intermediate, that comes from the elimination-addition mechanism. All right. So that looks like that's a wrap for this chapter. So a lot of new reactions that we've covered, a lot of mechanisms to help us explain regiochemistry and to explain different types of mechanisms, like the difference between elimination-addition reaction versus the nucleophilic aromatic substitution reactions. So if you guys have any questions or concerns about these mechanisms, obviously I'm here to help, so please reach out. I'll be more than happy to. So that's a wrap for this stuff.